looking at section 5.3, which is linear and exponential growth. And so you're going to look at some different applications and problems dealing with both linear growth, which you've already dealt with, finding the slope, and then exponential growth. So let's get started. It says here you're looking, I took the notes from the textbook. It says a linear function g can be written in the form mx plus b, g of x equals mx plus b. So you're familiar with that, the y equals mx plus b formula, where m represents the rate of change in g of x for each unit x increase in x. So m is the slope. And so if you look at this table, you'll see this is a linear function, and notice that they are going up, the y's, when you have a 1 unit change in x, the y's are going up by 2 each time, right? So we would say that the slope is 2. So each time x increases by 1 unit, g of x increases by 2 units, and so you can write the formula 2x plus 3 because the slope is 3, and then they give you the y-intercept as that first point. When x is 0, y is 3. Now, an go ahead. Oh, yeah. I'm sorry, I got a student here that can't see yet. So we'll try it now. This should come on. Is that good? All right, an exponential function is fundamentally different from a linear function because rather than adding a fixed amount to the previous y value for each unit increase x, an exponential function multiplies the previous y value by a fixed amount for each unit increase in y. In each unit increase in x. So what you see here, notice that it goes 3, 6, 12, 24. So 3 times 2, and then 6 times 2, and then 12 times 2, and then 24 times 2. So instead of adding 2, we were multiplying by 2 each time. Does that make sense? All right, and so the function that you'll use to describe it, this right here, this 2 is called your base. And so like if you wanted to describe this function, you could say that f of x is equal to 3 times 2 to the x. Because when x is 0, 2 to the 0 is 1, and so you do get 3. When x is 1, you get 6. When x is 2, you'll do 2 squared, which is 4, times 3, which is 12. Does that make sense? So this is called the base. That's the number that gets multiplied by each time. And this is your initial value, kind of like your y, well it's like your y-intercept, unless it's been moved somehow. So a function f represented by f of x equals c a to the x is an exponential function with base a and coefficient c. So this number is your coefficient. This is your c, and this is your a. And it has to be true that a is greater than 0, because it wouldn't make sense if it were negative. It would bounce back and forth depending on the exponent being positive or negative. So notice the big difference here is that the variable is in the exponent. Okay, so let's look at number 1 and see if we can figure out what type of function this is. All right, 243, and then 81, and then 27, and then 9, and then 3. Can anyone tell what the pattern is as the x's are increasing by 1 unit? Yeah, it does look like we're dividing by 3 or multiplying by 1/3. Does that make sense? Yes. Okay, and so using this formula, your c is going to be kind of the value when x is 0. So you can say a here is 1/3. And c is 9, so f of x is going to be 9 times 1/3 to the x power. And that's a little bit uncomfortable because, like, you have to do, if you wanted to check it, you would do 1/3 to the -3. But you remember a negative exponent means flip it, so that's actually 3 cubed, which is 27 times 9 is 243, if you just verify that. Let's see. So if you did, on here, if you did 1/3, so 9 times 1/3 to the -3, you will see that you do get 243. Okay? All right, so that was fun. How about this one? What does it look like it's doing each time? 729, 726, 723, 720, 717.
Rest is subtracting.
Yeah, it looks like we're subtracting 3 each time. So our slope is negative 3, right? So our slope is negative 3, and our y-intercept is which point? Which point is the y-intercept? Chilton, can you answer that?
720.
720.
Good, so 720, because that's when x is 0. So Marlon, can you give me the equation? I'll help you out. mx plus b.
So 720 times negative 3 raised to the x.
Yeah, well, what was this? What's your slope? What did we decide the slope was?
720.
Right here, are you, actually the
negative
slope
3
is
is
the change. Yeah, negative 3. So negative 3x plus the y-intercept, which is the 720. Does that make sense? You waking up?
Yes.
Okay, good job. All right, now let's look at another problem. It says, a company offers a college graduate $50,000 per year with a guaranteed 9% raise each year. Find a function f that computes the salary during the nth year. All right, well, what you might want to do is kind of think about what happens. What happens the first year you make $50,000, right? And the second year you make 9% more. So you're going to have 50,000 times, or 50,000 plus 9% of 50,000, right? So in year 1, when x is 0, you have just 50,000 is how much you make. In year 2, in year 0, okay, and then after the first year, year 1, you're going to make 50,000 plus 9% of 50,000. Okay, now in the second year, you're going to make this amount, whatever that is, and let me just for fun, let me write this equation as, I'll factor the 50,000 out, and that's 1 plus 0.09, right? So, and then the next year, you're going to make that amount, 50,000 times 1 plus 0.09, plus 0.09, 9% of this amount, which was the 50,000 times 1 plus 0.09. So what's happening is now you could factor this 50,000 times 1.09 out, and you would be left with 1 plus 0.09. It feels painful, but let me see if you can see it. Do you guys see that this term and this term are the same? So you could factor them out, and you'd have a 1 here, and then plus 0.09. So you would have the 50,000 times 1 plus 0.09, and what you would have left is, when you divide this function by what's in red, you would just have 1 left, plus when you divide this expression by what's in red, you would have 0.09. Well, so what do you notice? 1.09 times 1.09, that's the same as 1.09 squared, right? So that's 50,000 times 1, and this, I'm going to go ahead and write this as 1.09 quantity squared. And so in the second year, that's your formula. In the first year, that's your formula. In the 0 year, that's your formula. So in the nth year, it should make sense that it will be 50,000 times 1.09 to the n. Does that make sense? So the 1.09 is your base, and the 50,000 is your amount that you initially started with.
So if we go to the third year, is the power going to go up to 3?
Yeah, that'll be a 3. And I mean, you could do all this work again, but it's kind of tedious. It's better to just kind of see the pattern. Okay, so now they went ahead and they gave us 2 of the table values. They say that this is number 4 on your homework. All right, let's see what we know. We know this function, f of x equals ca to the x. Now, f at 0 is equal to CA to the 0, because that means plug 0 in for x, and you get exactly 17 when you do that. Okay? Now you can actually solve this, because anything to the 0 power is 1, except for 0, but we're not going to do that in this class. So C will be equal to 17. So you know what C is. All right, now f at 1 is 34, so let's see if we can use that information. Still using this same formula again, except we know now what C is, right? So we'll plug C in, and then a to the x. Now we'll use the other information. F at 1 is equal to the C that they gave us, or that we figured out, 17, times a to the first power. And that is equal to 34. Okay, and so then we can figure out what a is, because we will do a is equal to 34 divided by 17, which is just 2. Everybody okay? Kind of a two-step process. And so your equation, f of x, will be what? What do you think? Ebenea? Is she there? Can you tell me what you think the answer will be? I'm sorry, it's Danae. I combined your last name and your first name. Is that right? Evie is your last name, right? Do you want to talk to me?
Yeah.
I just feel like I don't know you. Someday we're going to be at Crackle Barrel and you'll be like, Miss Brooks, and I'm going to be like, I have no idea who you are. Your first name is Danae, though, right?
Danae.
Danae, okay. Danae.
Yeah.
Can you tell me the equation here?
17 times 2 to the x.
Perfect. Okay? Make sense? Because we found our C, we found our A, and we just plugged it into this formula. So it's very much similar to when you use y equals mx plus b and find the m and the b. Okay, this one's a little bit trickier because we love that one where when they give you the sort of like the y-intercept when x is 0, but they didn't give us that. They just gave us 2 random points. So we're going to have to do some thinking on this one. All right, we're again going to use our formula f of x equals CA to the x. And if I do the first expression here, I'll know that f at negative 2 is equal to C times A to the negative 2, which is equal to 4/5. And then the other equation, we are told that f at 2, which will be equal to C times A to the 2, is equal to 1/20. Okay, so you have to do a little thinking here. But you have 2 equations. You have this one and this one. And when you have 2 equations and 2 unknowns, you can solve one of the equations for a letter and then plug that into the other equation. So for example, I can take this equation right here and solve it for C. So what I would do to solve this equation for C is I will divide both sides by a to the negative 2. So CA to the negative 2 divided by a to the negative 2 is equal to 4/5 divided by a to the negative 2. Okay, now just breathe. A to the negative 2 in the denominator is the same as a squared in the numerator. So this is really C equals 4/5 a squared, because a negative exponent means move me. So you move, if it's in the denominator, you move it up to the top. If it's in the top, and you can move it down to the bottom. All right, now what I'm going to do is I'm going to plug what I found for C in to this second equation. Okay, this is called the substitution method. And then I'll just have one equation and one unknown. A will be my unknown. Okay, so when I plug this in, I'm going to have 4/5 a squared, that's the C, times a squared equals 1/20. Okay, does anyone help me simplify this? 4/5 a squared times a squared. How does that simplify? Chilton, can you tell me 4/5 times a to the what power? A squared times a squared.
It should be a to the 4.
Yes, a to the 4th equals 120. Good. All right, now, to solve for a to the fourth, first I need to multiply by 5/4 so I can make this go away. Or it's the same as dividing by 4/5. All right, and so then I get a to the fourth is equal to, 5 goes into 24 times, this is 1/16. All right, and then how do I solve for a? Anyone tell me how to solve for a?
Take the 4 cube root, or the 4.
Yeah, you're right. Good. Take the fourth root. So you raise both sides to the 1/4 power. And so you will get a equals, all right, 1/16 to the 1/4. What number to the 4th power is 16? Do you remember? Anybody remember? It's 2, because 2 times 2 is 4, times 2 is 8, times 2 is 16. So this is actually 1/2. But if you're having a bad day and you couldn't remember that, you can do 1/16 raised to the 1/4 power. And you get 0.5, and you can math frac that if you want. Okay, so now we know what A is. And once you know what A is, you're going to plug A in for C. I mean, into the equation here to figure out what C is. So this one is a lot more challenging. It's a lot of mathematical fun, don't you think? Yes, Ms. Brooks, is awesome. Okay, so this is going to be C equals 4/5, and then A squared, which is going to be 1/2 squared. So that's going to be 4/5 times 1/2 squared is 1/4, and then the 4's cancel here, and you get 1/5. So C is equal to 1/5. All right, finally now, we know what A is, and we know what C is. So we can plug it into our equation. F of x equals CA to the x is equal to 1/5 times 1/2 to the x. So that was a long one. Tricky problem. Lots of algebra to think about. Okay, let's talk about the graphs of these exponential functions. They ask you to graph it on paper. Of course, it's multiple choice, so I don't know. Maybe you will do that. Hopefully you will. If you were to graph something on paper, or, in the sand or something, what you would want to do is make a table of values, make some numbers. So -2, -1, 0, 1, 2 might give us a good idea. All right, so this is going to be 6 to the -2. Remember, a negative exponent means move me. So this is 1/6 squared, which is 1/36. It's a very small number. Then the next point is 6 to the -1, which is 1/6. And then when you plug 0 in, that'll be, 6 to the 0, which is just 1, and then 6 to the 1, which is 6, and then 6 to the 2, which is 36. So if you were going to plot this by hand, you would do -2 and then 136, which is an extremely small number, 1 divided by 36, 0.027. And then we go ahead and do 1 divided by 6 is 0.17. So at -2, it's just like you're just barely off the x-axis. And then at -1, you're just a tiny bit more. Sorry. Just a tiny bit more, but that's even kind of exaggerated. And then at 0, you're at 1. And then at 1, wow, you've grown all the way to 6. 1, 2, 3, 4, 5, 6. And I'm not even going to do at 2. I mean, you're just way up there. So what you find is that exponential functions grow very quickly. They have what we call exponential growth. And so this is easy now. We can pick choice, whatever choice that is. That one. Okay? Is that fun? Yeah, that was awesome. Okay, good. Let's try this one. Y equals 4 to the -x. Now, it's a little bit trickier because you have to deal with the negative, but you can handle it. You'll see that the graph is actually pretty similar. It just it goes the different direction. Okay, so we'll do points again. -2, -1, 0, 1, 2. So this is going to be 4 to the opposite of -2. Okay? So that is 4 squared, which is 16. Then you're going to have 4 to the opposite of negative 1, which is 4. Then you have 4 to the 0, which is 1. Then now you have 4 to the opposite of 1, which is, what is 4 to the negative 1 power? Marlon?
1/4.
Very nice. 1/4. And then 4 to the negative 2 power, Chilton?
1/2.
Careful. This means 1 over 4 squared. So that is what?
1/16.
There it is, 1/16. Okay, so this problem, let me just graph it, sketch the graph. At negative 2, we got 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Negative 2, we got 16. Then at negative 1, we got 4. At 0, we still had 1. And then it's like at 1, you have a 4th. And then at 2, you have 1/16. So we've got this function here. Like that, right? So that looks like this choice. Let's see. Wait. Oh, they're kind of crammed together here. It's this one. Okay? This is for the next one. Y'all ready to steal it with your graphing calculator yet? So we'll say, yeah, whatever. Just kidding. I'm sure you should do all of these by hand like it says. Okay, but I'm going to save time. This is going to be 1.6 raised to the x power. And then I'm going to do the same window that they have over here. Notice they have -5 to 5, -5 to 5. So I'm going to change my window. I'm going to do -5 to 5. I'm going to count by ones. And then -5 to 5. Let me graph it. There it is. Okay, that looks very much like this first choice right here. Are y'all having fun? Yes? Me too. I'm feeling kind of crazy today, like, I don't know. I think it's the weather. It was 48 when I got in my car this morning. Well, it was like at 4 when I was going to run, but it was early, but it was cold. I love the cold weather. Uh-oh. I mean, it was even cool right now when I was driving in. Okay. It says use the transformations to help you graph 3 to the x plus 1. Okay. Who's got, I guess do I have a, I don't have an in general sort of statement. These functions, what you must notice about these functions is that it could never be negative. So let's just make a note. If f of x is equal to ca to the x, and a is greater than 0 and not equal to 1, because it's boring if it was equal to 1, then the function has a horizontal asymptote. And I guess I want C to be positive too. At y equals 0. Because it'll never be 0. I mean, it'll never cross the y-axis. I mean, the x-axis. It never crosses the x-axis. Even if a were negative, then it grows this way. So this is when a is positive. If a is negative, it goes like this. Oh, sorry. They can't, it's impossible for them to be, for the y value to be below the x-axis, because you know that a is positive, and if you know c is positive, there's no way that's ever going to be negative. So we have a horizontal asymptote at y equals 0. Now you can do a reflection and a shifting to make the horizontal asymptote different. So for example, what do you think this function, how do you think this function is changed? 3 to the x plus 1, what happens to it? Chilton, you seem to be smiling. What do you think? 3 to the x plus 1, how does that change the graph? What happens to it? How is it different than 3 to the x?
It goes left 1.
Yeah, it's shifted how much?
1.
And in what direction?
Negative. Left
Shifted up how much?
1.
1 unit? Does that make sense? Because of this plus 1? Okay, and so your horizontal asymptote now is going to be, instead of y equals 0, it's going to be y equals 1, which is this one. Now, it's still going to grow fast like that, so it's clearly going to have to be choice A. Shifted up 1. So what used to be at the point 0, 1, this is 0, 2, because this is counting by 2's. And then you can see that horizontal asymptote at y equals 1. These others are just silly. They're not even close. Okay. All right, here's a new number. It's called the number e. It's an exciting number. It's kind of like pi. Shows up a lot in life. One definition of e is to look at the function, look at the equation 1 plus 1 over x to the x. And what you do is you consider that limit as x goes to infinity, which means as x gets bigger and bigger, where does this function go? What number does it approach? Now, this always freaks me out, so it's a good sort of Halloween question, because it seems to me like if x were 100, 1 over 100 is 0.01. If 1 over 1,000, 1 over 10,000, 1 over 1,000,000, this number right here is going to 0. So if I do 1 plus pretty much 0 to any power, it seems to me like that would be 1. Like if you have 1 plus 1 over 1,000,000 to the 1,000,000th power, it just feels like it would be really close to 1 to me. Do you know what I'm saying? Because it's basically just 1 to the 1,000,000th, which it seems like it should be 1. But if you do a little bit more investigation with your calculator, and you do 1 plus 1 divided by x, and you raise that to the x power, and you go to your table, and you type in really big numbers, like 1, 1,000, 10,000, 100,000, notice you don't get 1, but you get this number 2.71828. See those numbers there? And that is exactly, see here at 1,000, 2.71814. If you do it 100,000, 7182. And so it actually is this number e, which is irrational. It looks like it's repeating, but it doesn't. It doesn't repeat. It's an irrational number. It's kind of like pi. So it shows up in nature a lot, and it's named after Euler. Euler first found this number, E-U-H-L-E-R. So he gets credit for just calling it the little e. Okay. So what we can do now is we can let that e be a base, and we call this the natural exponential function. So instead of 2 or 3 or 1/2 like we were doing, we let e be the base, and that's the natural exponential function. Okay, so we can't do this by hand. We have to use our calculator. So let me show you where your e is on your calculator. If you look at your calculator, you will see the e to the x function is the second function for the ln button. Do y'all see it? So if you do second ln, then you can raise e to any power. So in this case, 1.1 is what we'll raise e to. And we'll hit enter, and that's what we get. 3.004166024. Okay. 3.004166. And so, I mean, it should kind of freak you out because e is a number that's irrational. It never repeats or terminates. How do you even raise it to a power? So to answer that without your calculator, you have to do calculus 2. So this is a kind of a little hope that you might consider taking a calculus class. Okay. Now, we have some exponential functions are used a lot in banking industry. So I'm giving you two formulas that are used in the banking industry. There's the compound interest formula where you're compounded a certain number of times per year, like quarterly or monthly or semi-annually. So semi-annually, your n equals 2. Quarterly, your n equals 4. Daily, n equals 365. Monthly, you get the picture, right? N equals 12, right? Biannually would be n equals 2, twice a year. Annually, n equals 1. So we have that formula. And the big thing for you to remember when you're working with this formula is that the R has to be expressed in decimal form. Like if it's 5% interest, you want to write that as 0.05. Otherwise, you screw up the formula. Okay? And the principal is the amount that you invest. Like if you have $100 and you put it in the bank. Okay. Now, the continuously compounded interest formula, it's the PERT formula, and it uses this E. So this is if, like, it's just constantly, the bank's just constantly giving you interest, which is what most banks do. They compound it continuously. And if that's the case, then remember we talked about this function that what happens is this X goes to infinity, quarterly, daily, hourly. If this goes to infinity, well, then you get really close to the number E. So that's why that E comes in there. All right, so let's look at some examples. So suppose that $6,000 is invested at 6% interest. So immediately in your brain, instead of 6%, you are thinking what? Good, 0.06. And you find the amount of the money in the account after 5 years. So this is your time. This is your initial amount. So this is your P. If the interest is compounded annually, that means that n equals 1. It's just once a year. And then we have two questions, because then in a minute they want us to do it continuously. So let's do the first part and then the second part. Okay, so annually, you'll use your first formula. A equals P times 1 plus R over N to the NT. So here, your P is 60,000. And it's 1 plus 0.06 divided by n, which is 1, to the n times t, which is 1 times 5. So on this one, you can just write it as 60,000 times 1 plus 0.06. So you can just, if you see, that should be 1.06 to the 5th power. So we can type that into our calculator, 60,000 times 1.06 to the 5th power. And we get $80,293. 0.53. Okay, now, continuously. All right, the formula is A equals PE to the RT. Your P is 60,000. E to the rate, which is 0.06, to the time, which is 5. And let me show you on your calculator, you have to make sure your exponent is in parentheses. So you're going to do 60,000. And then you're going to do times E to the 0.06 times 5. And then you close the parenthesis. Okay? And you should get $80,991.53. Okay, who wants, which way would you prefer for the compounding to be? Obviously. Or maybe not, since it's not responding. What would you rather? If the bank offered you two deals, which way do you want your interest calculate?
Continuous.
Yeah, continuously, because it's about $700 more. So, okay, so how about the next one? It says, suppose that $9,000, or $90,000, that's your P, is invested at an interest of 7%. Immediately think 0.07, that's your R. Find the amount in the money after 9 years, that's your T, if the interest is compounded annually, and then compounded continuously. So this is pretty much the same question. A equals 90,000, 1.07, because it's annually to the 9, versus A equals 90,000 e to the 0.07 times 9. Okay, so I want the audience then to give me these two answers, please. What we got? Anybody?
For the continuous one, I got 168,984.95.
Okay, so I can just enter here and change this one to a 9 and this to a 7 and that to a 9. And so you got how much? 168,984.95? Good.
Yep.
All right, and anybody want to tell me what they got for the annual interest rate?
165,461.33.
Okay, let me see. I forgot to put my parenthesis in here. My little pen doesn't work as well on the calculator. That sounded like it came. Is that Brett?
Yes, ma'am.
See, I know your voice, I just don't know your face. Okay, 165,461.33. 165,431.33. Oh, 461. Okay, good. All right, now you can also have exponential functions that maybe look a little bit more challenging, but I love these types of functions. I don't know if you guys took any kind of standardized tests. Whenever they give you the formula in the question, I'm always happy because then all I have to do is plug something in. Okay, so it says the number of grams of a certain radioactive isotope substance present at a time t is given by the formula A equals 600 e to the negative 0.007 t, where t is the number of years. Find the number of grams that are present at time t equals 0 and at time t equals 900. Oh, well, that's easy, right? We're just going to put 0 in for t and find the answer, and then we're going to put 900 in for t. So I'm going to do the easy one, which is putting 0 in for t. This is going to be e raised to the negative 0.007 times 0. That's just 0. Anything to the 0 power is just 1. So this is just going to be 600 grams is the initial amount that's present. And then after 900 years, I'll let Chilton tell me how much it is after 900 years.
600.
Is it 1.10?
How much?
1.10?
1.10, let me see. So 600 second e to the negative 0.007 times 900. Yeah, 1.10, I don't know, 2? 1.102. Is that right? Yeah, grams. Okay, so that was fun. All right, now, here, this one might be a little bit tougher. It says the table lists future concentrations of a certain greenhouse gas in parts per billion if current trends continue. Let x equals 0 correspond to the year 2010. Okay, so this is 0. And x equals 20 correspond to the year 2030. So like this will be 5, and this will be 10, and this will be 15. Find c and a so that f of x equals ca to the x models the data, and then you estimate the gas concentration in 2026. Okay? All right, now, you have this formula f of x equals CA to the X. Now, we know that the C will be the amount that's present at time 0. And so in this case, since f at 0 is equal to C, we don't know, A to the 0, but we do know the answer is 0.67. This implies that C equals 0.67. So since they gave us the initial amount, then we can immediately figure out what C is. Then we can use any of the points to figure out what A is. So now we have an equation, f of x equals 0.67 A to the x. So we can just use any of these other coordinates to try and figure out what A is. So I'll go ahead and pick the 5. So I'm going to say f at 5 is equal to 0.67 A to the 5, and that answer is 0.78. So in order to figure out A, I do A to the 5th equals 0.78 divided by 0.67, and then I'll raise that to the 1/5 power to solve for A to the 1/5 power. And it's probably going to be a decimal, 0.78 divided by 0.67 to the 1/5. I don't think it's going to be a real, oops. I don't know how pretty an answer it's going to be. Yeah, 1.03 we could probably use as our A. So this is approximately 1.03. Okay, and so our formula is f of x. It depends on what they tell you to round it. I don't have the answer here. I don't have the little box, but pay attention to the rounding. So this is going to be 0.67 times 1.03 to the x power. That's your formula. And then the concentration in 2026 is going to be when x is 16. So 2026 implies that x equals 16. So f of 16 is going to be 0.67 times 1.03 to the 16th. So we'll try that. 0.67 times 1.03 raised to the 16th power. So 1.075. Now, just watch this watch the rounding on this, because it can, because I rounded that 1.03, keep the rounding to what they tell you. Okay, following an unexplained decline in the number of birds of prey on his property, a farmer sees a drastic rise in small mammal population. Small mammals, what are those? Yuck. Rats or mice, right? The function m of t equals 500 times 1.3 to the t can be used to estimate the number of small mammals on the premises. Yuck, 500 is initially. T years if hawks, owls, and similar birds fail to return. Estimate the number of small mammals in the area 5 years after the birds decline. So we'll put 5 in for t. This is going to be really bad. M of 5 is going to be 500 times 1.3 to the 5th. Sounds like you had a bell. I'm just going to finish up here. Okay, so this is going to be 500 times 1.3 raised to the 5th power, which is 1,856 rodents. So m equals 1,856. Okay, now your graph is going to grow really, really fast. And so it's going to be this one, choice A. You can type it in your calculator, but notice your window. You're going to have to get really big on your Y. Now, let's look at, I think this is the last question. Okay. Under certain conditions, can you guys mute, Chilton, because I can hear your bags moving and stuff. Thanks. Under certain conditions, the number of bacteria present in a colony is approximated by this formula. And it says, if A naught is 2,800,000, find the number of bacteria present at 5 minutes, 10 minutes, and 60 minutes. Okay, so what you can do on this one is you can actually use your calculator to help you. F of t is equal to 2,800,000 times e to the 0.022t. So what I would do, since there's 5, 10, and 60 minutes, since there's 3 that I have to do, I think I'd use my table to help me get this. So I'll go to y equals 2,800,000 and then e to the 0.022 x. All right, and then if I just go to my table, I can type in the different numbers that I need, which would be 5 minutes, 10 minutes, and 60 minutes. Okay, now notice these numbers. This e to the 6, what does that mean? Well, that is 3.13 times 10 to the 6. Notice when I moved my cursor so that it was sitting on top of this number that I thought was weird, it shows up down here. And see, if I go down, then I'll see it down there. Okay? So you can see more decimal places in the bottom there. So after 5 minutes, it's 3,125,578, and then after 10 minutes, and then here it is after 60 minutes. So I'll just take these numbers here and pop it here and let you kind of figure out the rest of that. Okay, now this last question looks like it was a question that we just talked about, but anyway, it's a very similar question. They give us the equation. Is it exactly the same? Yeah. So I'm going to think that you can do this question because I just did this question. But basically, you're going to pop the 4 in there and figure out how many mammals you have, and then pick the correct graph, which I bet you can pick is right here. So I'll let you finish that one. Okay, you guys have a good afternoon.